There have been an enormous number of wonderful, really revolutionary developments in these subjects of geometry and topology in 3 dimensions over the last 30-odd years. And even an astonishing number of new things have been learned since the turn of the century. And what I want to do tonight, maybe a little bit ambitious, but I'm hoping to take you on a whistle-stop tour through some of the ideas that have been involved. But in order to tell you about what's happened in the last 15 years, really I need to start by going back to the turn of the previous century, and we need to look at some of the things that were going on then to explain a little bit about geometry and topology as it was at that time, and we'll see how that gets carried over. So the plan of my talk, we shall first see a little bit about what is hyperbolic geometry. That's the geometry that a lot of these developments are based on. What is this word topology? Surfaces, I'm sure everyone knows what a surface is. We will then move on into 3D, and then we get to the sort of late 1970s. A complete revolution happened with the American mathematician Bill Thurston, and so I want to give you, at least try and give you some sense of the enormous strides that Thurston introduced. And then since the millennium, there have been further enormous strides, which in some sense have completed a large part of the programs that Thurston initiated. So I want to try and give a flavor of that. And then finally talk a little bit about an open problem, which I think is very fascinating and which touches on the work that I've been doing, and which also relates to some of the ideas I shall be telling you. So that's where we're going to go. So hyperbolic geometry. If you think about geometry, at the end of the 19th century, there was a lot of discussion, what is geometry? You could say geometry is study of space. Well, we're going to start in 2 dimensions, space in which wherever you are and whichever direction you look, what you see is kind of the same. So whatever it is, it looks the same everywhere. And of course, the most obvious kind is ordinary Euclidean geometry. But you might also be living on the surface of a sphere, and wherever you are on the surface of a round sphere, things look the same. They don't look quite the same as if you're on the flat, but they look the same. And the third kind, the kind that was missing up to about 200 years ago, is called hyperbolic geometry. So here's a picture that shows rather well Euclidean geometry. Everybody knows the sum of angles in a triangle is 180 degrees. In a sphere, well, what are the straight lines on a sphere? They're the great circles, the way airplanes would fly to go the quickest way. So the great circles on the sphere, and if you start playing around drawing triangles on a sphere whose sides are great circles, you very quickly come to the conclusion that the angles add up to something greater than 180. How much more than 180 depends in a very precise way on the area of the triangle. And the third kind of geometry then is the kind where the sum of the angles in a triangle is less than 180. So there's a kind of pairing between these two things. So hyperbolic geometry you can think of as geometry on a surface which is everywhere saddle-shaped. So you see in this picture, it sort of curves down that way and then over a hump in the other direction. So a surface of negative curvature. Hyperbolic geometry was first discovered in the search for a proof of Euclid's parallel postulate, but rather than finding a proof, a whole new world of geometry was discovered, and we can nowadays interpret it in this rather nice way. So how are we going to model this geometry? You can't put the whole sort of plane of this geometry into ordinary flat Euclidean space because it's too big, basically. So this is one of a rather nice series of Crochet models that's been developed by this person, Diana Tamina. There's, in fact, a whole book you can buy about making crochet models of geometry. There's a whole project which has made a coral reef out of crochet, which I think is in Dublin, I'm not quite sure. Anyway, you can make these models, and the main point is once you start trying to make a surface that's curved the right way, it starts crinkling up, and if you kept on before too long, you would find it was just so crinkled around the edge that you just couldn't fit it in there anymore, and you would just have to stop because you wouldn't have any more space to make your stitches, basically. So here's another way to do it, which perhaps some people may be familiar with. So if you know anything about the theory of special relativity, you can use the space in which special relativity takes place, and I'm talking about a two-dimensional. Usually one has 3 dimensions of space and 1 of time. This, we're just going to have 2 dimensions, x and y of space, and this is time. And this picture over here on the left is a rather nice model made by a colleague. So this is the shape on which geometry takes place, and let me just go on, and it's not so easy to understand geometry there. So rather than doing that, we project it. So just as you can think about geometry on the surface of a sphere and project it onto the flat plane, so we can take geometry on this shape here with this rather curious formulas, and we can project it onto this circle. And this is the first time Poincare's name comes up. His name will come up repeatedly through the talk. We project it onto this circle. Now, I didn't say, but a shortest distance path on this thing turns out to be the intersection of a plane through the origin with this hyperboloid, this blue object. And when you project it down, what you see is you see a disk here, and you see these lines. So these are shortest distance paths, sort of straight lines in this geometry. And what they look like in our map projection is arcs of circles that hit the boundary at right angles. And so things are very distorted, but angles are correct. So that's good. Of course, there are precise formulas for all this, which I'm not going to try to explain tonight. There are formulas. And the main thing to remember that this is like a very distorted thing. Like when you project onto a flat atlas, things are completely distorted up near the North Pole. They're very wrong. So don't think that this is a correct picture. But nevertheless, let's carry on and talk about tilings. A lot of what I want to say is connected with tilings. So everybody knows how to make tiling patterns in the ordinary Euclidean plane, kind of thing you play around with at school. And you can make tilings of the sphere. This is another nice model made by Henry Siegermann. So here is a sphere with a tiling pattern on it, and he's rather nicely projected it in this photo onto the flat plane. And of course here you can see here's a sphere, well here's everything distorted. So we kind of see the idea of distortion in a projection. What about tiling the hyperbolic plane? There is a picture of a tiling of the hyperbolic plane. And the thing to take in here is that although these shapes, they're actually heptagons, although they look different, actually, from the viewpoint of this geometry, they're really the same. So in other words, just as in the hexagon picture, every tile is identical to every other one, there's a rigid motion of geometry that carries one to the other. The same thing is true in this picture. One thing about this picture is that if you count the number of tiles around here, they increase linearly as the radius of your circle. If you count the number of tiles here, you find they increase exponentially fast, and that's related to this crochet surface that I had that was all crumpled up. There's more and more and more of them, and there's an infinite number of them to get from here to here. It's an infinite distance, and this rather wonderful little video clip shows you probably better. It's going very fast, but there we are. All of these shapes are the same, and we're zooming on. Peter Lieper is another computer graphics person who's got kind of fascinated by some of the things that can be done in mathematics. So this is a picture, and as you see, we go on and on and on forever, and out at the horizon it just goes on, and it's infinitely far away. So that's my very quick introduction to hyperbolic geometry. We're going to come back to this geometry repeatedly. Let's go on to what the word topology means. So topology, what is it? It's the study of things that remain invariant, unchanged when you do deformations. So here is a picture of what do I mean by a continuous deformation. Well, I take a thing and I squish it and I scrunch it and I pull it, but I don't rip or tear it. And I want to ask what remains the same. Well, if you like, the fact that there's a little hole that I could sort of go through here between her back and her front, it's still here, even though things are a bit kind of distorted. Well, there's more the same in these pictures, but you could distort much more than that. So that's what topology is about. And well, again, the name of Poincare comes in, so let me introduce Poincare. I'm sure many people here are well acquainted with Poincare. He was really one of the absolutely great mathematicians of all time, mathematician in mathematical physics. He contributed to enormous numbers of different areas, and in particular, he's often known as the father of the subject of topology, although he wasn't quite the first person to do it, but he was really the first person. He introduced an enormous number of ideas that are still the fundamental tools of this subject. He also, of course, was the person who wrote down the Lorentz transformations in their modern form, which are used in the theory of relativity, special relativity. He was the person who probably can be credited with the invention, in some sense, with the invention of what we now know as chaos theory. So many, many things, and I rather like this quotation, which I'll leave you to read. Felix Klein was one of the leading German mathematicians at the sort of later part of the 19th century. Klein actually drove himself into have a breakdown trying to compete with Poincare, and eventually, I think, gave up and realized and wrote a lot about Poincare in this rather wonderful tribute. So this is Poincare, and as I say, his name is going to keep continually cropping up throughout the evening. So what about surfaces then? What can we say about surfaces from this viewpoint of topology? And perhaps by the time I've said it, you will have a bit more feeling. So the idea is it's easier to see a picture. Here's a surface. Now, if you take a loop, a closed loop on this surface that just kind of goes round it once here, and you cut it, of course, it'll come apart. And what will it look like in topology? Well, it'll be like a cylinder, but a cylinder is really the same thing if I took a sphere and I cut two disks out of the cylinder, and then I squashed it. So from the viewpoint of topology, if I make one cut through this thing, I get a sphere with two holes. And if I took this one and I cut each one of the two handle things with a cut, and I opened it out, I would find I had a sphere with four holes. And if I did it on this one, I would have a sphere with, I think, 6 holes. So here's another one. You might think this one is different because it's all twisted up. It's still like this, but it's all twisted up. But it's only twisted up from the viewpoint of how it's been put inside three-dimensional space. And the classification that we're talking about doesn't see how it's sitting in three-dimensional space. Still, if you made one cut, it would still fall apart into this sort of cylinder with two ends, so it's still a torus. So the way we classify surfaces, here's a rather beautiful, I think this is a bronze cast. It's not very large, I think, the real thing. Carlos Sequin is another of these kind of computer people with a very artistic bent who makes rather wonderful representations of topological objects. So it's much harder to see this has got two, you can see it's got some holes cut in it, but it's harder to understand it's got its genus 2, but let's believe that's what it is. So that's surfaces. And it took, I've told you this in a couple of minutes, it took a long time to sort all this out. So this is not meant to be obvious. Depends what you think a surface is to start with. Anyway, that's surfaces. Now, we're going to now go into geometry on surfaces. What can we say about geometry on surfaces? So this is one of the very important ideas in this talk, and one of the important ideas in the, I could say really in the modern study of topology. What's a geometric structure? So supposing that I've got some object, and supposing that in a little region around where I'm standing, I can manage in some way to measure distance and angles in such a way that it looks identical with a bit of one of these basic geometries I've talked about. So it might look a bit like this flat Euclidean geometry, it might look like a little piece of sphere, or it might look like a little piece of hyperbolic geometry. So a sphere, well, everywhere I stand on a sphere and I look around me, I see a little piece of a sphere. So that's not very exciting. What about a torus? So I'm sure that you've seen pictures like this. You take a rectangle of paper, you glue two sides together to make our cylinder. Here's our cylinder. You pull the two things round, you stick them together, and lo and behold, you've got a torus. I'll tell you where this picture came from later. Okay, so we can make a torus. Actually, there's a sort of cheat in this, because, of course, I can roll up and make a cylinder. If I try and to do this part, actually, if I try and do this in 3D, naively, plainly, the thing is going to all crinkle and crunchel up. It's not going to work very well. So there is a bit of cheating here, but it's not really cheating, because what I'm talking about is what you would see if you were a fly. This is a kind of abstract concept, if you like. If you were a fly living here, well, actually, or if you even was a fly and you walked across this line, it would be no different from going across here and then coming back in here. So somehow there is a meaning to saying this thing is basically coming from a rectangle cut out of Euclidean geometry. So the torus has got Euclidean structure. So here's a picture. I take my square, but then if I went across this side, I kind of unfold it and see another copy of the square and another copy and another copy. Well, really, I translate it, but let's not get too detailed here. So here is another picture. Here's another picture of gluing up this torus. And there's one very crucial feature in doing this, that it was very important that when I glued, well, first of all, when I glued from here to here, that this plus that were 290 degrees, so they made 180 degrees, so they met at a straight line. And then when I put the two ends together, I've got two lots of 180 degrees, and that those add up to 360, and that makes a nice, smooth, flat piece. It makes 360 degrees, and that's fine. So there is what we mean by saying a torus has a Euclidean structure. So I've somehow to this surface attached a natural notion of Euclidean geometry. Well, what happens if I now go to a surface which has got 2 holes, genus 2. So here is a picture. If you follow through this, if you were to glue the opposite sides of this thing together, you can go home and puzzle about this for a long time. But it is true, I assure you, that if you glue the opposite sides together, you're going to have to kind of come round yourself, maybe go through yourself, depending how you do it. But you should, in the end, be able to convince yourself that if you glue it up, you come out with a thing like this. Okay, so let us believe that. But the trouble is, if you took an ordinary octagon, then 8 of these corners have got to meet up here. And whatever the angle in an octagon is, I think it's 135 degrees. Anyway, if you glue 8 of them together, there's no way it makes 360 degrees. It's way, way more. It's too much. So you glue them together, and the angle is much too big, so you haven't got a nice Euclidean structure, because if you try and cut it out of a piece of paper and glue it up, at the last minute you'll have a nasty mess in the middle where it doesn't fit together flat. So what are you going to do about it? Well, you remember that in hyperbolic geometry, the angles in a triangle don't have to add up, or don't add up to 180. They add up to something less than 180. And actually, you can create triangles whose angles add up to anything you like, less than 180. And here is a rather beautiful tiling of the hyperbolic plane, in which we've got a nice regular octagon, and the angles here have been manufactured each to be 45 degrees. So when I stick 8 of them together, lo and behold, I make 360 degrees. So it's nice and locally making the right angle that it should do. And so I've created a surface. If I could cut this piece of paper out of hyperbolic paper, which has got this kind of curvature, and if I could stick them together, I would have created a surface of genus 2. And actually, by just adjusting the angle using this trick, you can make a surface of any higher genus you like. And this was, I suppose, known and understood. It was being studied a lot in the 1920s. And you might say, well, so what? Actually, it became very important, because anything you want to study about this surface, you want to know what closed loops are on it. Somehow, if you look at this pattern, this rather complicated but beautiful pattern, you can read off all sorts of things here. And one thing you can do is you can study particles sliding around on this surface. And it turns out that by studying the intricacies of this pattern, and by realizing that things, geodesics in this hyperbolic plane, they come close together and then they kind of diverge from each other. And that's the essence of chaotic motion. So sliding around on one of these surfaces is a prototype for what we now call chaotic motion, and this was one of the first examples that was really studied and introduced the idea of randomness and chaotic motion, but by a perfectly well-defined formula. So this was in the sort of 1920s and probably 1930s for that. So let me just recap very fast. We have learned that we know how to classify surfaces, and every surface in a natural way has got a geometry on it. It's either like a sphere or it's like a piece of Euclidean plane, but usually it's like the hyperbolic plane. Right. So now we are set to proceed into 3 dimensions. So my first problem in this is there is not a normal English language word for the 3D analog of a surface. Nobody's yet come up with a very good word. So a thing that's an analog of a surface, but in more dimensions, is known to mathematicians as a manifold. So we talk about a 3-manifold. So what it means is everywhere you look in a little bit, it looks like some sort of very squashy, vague version of 3-dimensional space. But it's got all sorts of complicated loops and tubes and holes and goodness knows what in it. So some very complicated thing. Well, we've just seen how to make a surface by gluing up the sides of a hyperbolic octagon. So supposing we took a hyperbolic polyhedron, and supposing we glued up the faces, if we were lucky, we could fix the angles so it would all work, and they'd have to fit round the edges nicely, and they'd have to fit right at the corners. But if we were clever, we might be able to do it, and we might be able to produce one of these three-dimensional objects, which, just in the same way that we glued up in 2D and created a surface of some genus, we can create something in 3D which we can say has a hyperbolic structure, and it comes from this process. And now we come to some really amazing pictures. Just as in 2D, we could kind of unfold the thing, the torus, into a square tiling. So in 3D, we can start with, for example, this, which is the same as the one on the previous slide, and we can unfold it into a tiling of three-dimensional space. So I don't quite know how to make a drawing like this. I think it's amazing. But anyway, so here we are. We've got the walls of this thing have been made transparent so you can see, and you're sort of seeing through to the cells, if you like. So you could imagine a sort of a cubical tiling of ordinary Euclidean space. This is an analog in hyperbolic space. And Joss Lays, by the way, has a rather nice website with all sorts of pictures. In particular, there's a whole section of rather wonderful tilings of hyperbolic 3 space. Okay, so hyperbolic geometry in 3D, well, it produces some pretty pictures. Okay, right. Okay, before I can go on, I have to give you an alternative viewpoint. If you go back to my original picture about hyperbolic geometry sitting inside the Minkowski space of special relativity, if you look out to infinity along the light cone, you see a sort of, in 2D you see a circle, in 3D you'd see a sphere of stuff that's way out at infinity. And I also said we can model two-dimensional hyperbolic space as the inside of a disk, so not surprisingly you can put 3D hyperbolic space inside a sphere. So far, so good. So here is a picture, another picture by Joss Lays. This tiling that we saw, you could stand sort of on the outside of the universe and look in, and you would see something rather wonderful like this. Poincare, I guess when he was working with these Lorentz transformations of special relativity, realized that the isometry is a word I haven't used. Isometry means a rigid motion, a congruence, things like that are like congruences in Euclidean geometry. So isometry means keeping the distances the same. So we have something, a rigid motion inside hyperbolic space that's moving tiles to other tiles, but actually it does something to this sphere at infinity. And on this sphere at infinity, you can calculate the formula. Now, it's a formula on a sphere, but no doubt some of you know how you can think of the sphere. You can project it from the top onto the plane, and you can think of the plane in terms of complex numbers, x plus iy, and so if you take the plane together with one point at infinity, you've made a sphere. So you can kind of it's really like stereographic projection, nothing more than that. So you can translate the formulas into some simple formulas with complex numbers, and we can write down the effects of an isometry of three-dimensional hyperbolic space inside the ball. We can write down the effect out on the boundary, and this formula, the beauty of this formula is it's just a 2x2 matrix, or a nice formula like that, and we can just multiply 2x2 matrices and do all our calculations. So instead of having to have some quite complicated 3D stuff, we can work in 2D. And yeah, there we go. now we can see what I'm doing now is I'm showing you the effect of a particular isometry of three-dimensional hyperbolic space, but I'm just looking out at infinity and watching what it does out at infinity. So this man is getting transported around, and that's while we're watching him, waiting for him. Here's the formula. So I just want you to remember this for later on. I'm sure everybody will remember this. A plus D is an important quantity. And why is it important? Well, you can see that this person is going around in spirals, and he goes forward into a kind of sink, and he goes backwards into a sink. So there's a forward sink and a backward sink. And in 3D, what's this isometry doing? There is a hyperbolic geodesic going from a line going from one end to the other end. So it's a sort of piece of circle orthogonal to my boundary sphere. And this transformation is pushing along this axis and twisting as it goes. So it pushes along, and the twisting is, you see that effect in the spiraling. So that's what one of these mappings does. So it's very important. When you look out at infinity, all the facts about being rigid motions go away, but still a lot of good stuff remains. And just think about this kind of motion along an axis that you translate and you rotate, and that can be read off from this A plus D number called the trace. Okay, so now I need to introduce another idea. That was one isometry. Supposing I had two or several isometries, and supposing I do a bit of one and a bit of another and a bit of another and a bit of another. I keep going with them, and I allow them to go backwards as well, and I pick up a picture of this poor man, and I transport him around. This particular one he's got one thing that's pushing him one way and another thing pushing him another way, and he gets twiddled around. And what happens, instead of there being just two fixed points, a source and a sink, there are actually a whole continuum of sources and sinks, well, a whole countable number of sources and sinks, and you can see his images get smaller and smaller and smaller, but they go all the way around the edge of this thing, and this thing is called the limit set of this collection of matrices. And you can also think of it as the chaotic set. When you get to that level, everything's moving around chaotically. In fact, you don't quite see it in this picture, but this boundary here is a very complicated and rather beautiful fractal curve. Now, I'm not really going to go into this too much this evening, but I wrote a book some years ago with these other people, and David Mumford is a very brilliant mathematician. David Wright was originally a student at Harvard. He's also a number theorist, but he's extremely good at computing. We wrote a book explaining how you make pictures like this, and in particular, a number of people have taken that up. In particular, Joss Lays used some of our recipes, and that's how he created some of his pictures. So let me now start. I can now start telling you some more recent mathematics. And the first thing I'm going to tell you is about hyperbolic manifolds whose volume is finite. Right, well, I take a finite sort of original tile or cell, a finite size, and I glue up the side, so what I get is a finite size. So that's what we're talking about. And we assume that this thing is glued up so there's no boundary anywhere. And now, there's something about 2D I didn't tell you. If I make, for example, a torus by gluing up a rectangle, I can make it a long, thin rectangle or a short, fat rectangle, and I can actually skew it into a parallelogram and still glue up the sides. So I can do a lot of things, and it'll still be Euclidean, but the tiling of the plane will change. And it turns out in 2D, you can always do that. There's a whole science called Teichmuller theory about how you can deform geometric structures on surfaces. In 3D, a theorem, a famous theorem called the Mostow rigidity theorem, says in 3D you can't do that. Things are fixed, they're rigid. So what does this thing say? Supposing I've got two of these finite volume manifolds, and supposing, well, for the mathematicians, supposing their fundamental groups are abstractly isomorphic, but imagine not all of you are mathematicians. So supposing they're topologically the same, somehow you know that you can squish one and do all kinds of mess to it, forget the geometry altogether, and you can get to the other one. Actually, then they're really the same thing. They're isometric, so rigidly you pick one up and it's exactly the same as the other one. So that's what Mostow's theorem says. And now I'm going to talk about something else. So that was a tile which was finite volume. I've been more concerned with tiles which have got infinite volume. So here's a picture in 2D. So this particular yellow tile, you can see it goes all the way out to infinity, and there's a kind of thickish piece that goes out, and that means it's got infinite size. And here's another picture. Now, this picture is what you see at infinity from a 3D tile. So imagine I've got my hyperbolic space inside the ball, and I'm kind of looking through from the outside in, and there's some complicated basic tile, and it hits the boundary at infinity, and then you can take all the copies of it, and so I tile the stuff at infinity. So that's what you're seeing in that picture. And you can see how the tiles get smaller and smaller, and of course what do? They pile up on this same thing, the limit set of the group. And if you would take this stuff out at infinity, you could play the game of gluing up the sides of the tile, but now we're distorting things by these Möbius maps that have forgotten how to measure distance, but they do know how to measure angles. So you can think that whatever it is I mean by Riemann surface, it's a kind of structure that's like geometry that only remembers angles. And there was a great deal of work in the 50s and 60s studying these things. And here's another famous theorem. It's a bit like an analog of the Mostow theorem. It says that if I stick up these things, then if I control what happens out at so there's a tile, and in the middle of hyperbolic space, we glue up the sides of the tile, and we produce a solid thing that has some bit that goes off out to infinity. And out at infinity, we have this floppy tile that's glued up, which only remembers angles. And what Bayer's theorem says is, if I know what happens to the angles, the stuff out at infinity, and I know that for every part of the tile that went out to infinity, then I know everything. Then it's fixed. So it's sort of like an analog of Mostow's theorem. So hyperbolic manifolds, we can think of finite volume, we can think of ones with tiles going out to infinity. And then there's a rather subtle distinction that probably kind of lost at the moment, but anyway, you can have finitely many sides or infinitely many sides of the tile. So what should we know? Well, there's a tile with an infinite number of sides, and we're sitting inside a tile. It actually only takes two transformations. You wouldn't quite believe it, but because of spiraling that you don't really see, it actually only takes two isometries to glue up all of this stuff and make some complicated manifolds. So what was known? Well, we knew this wonderful Mostow rigidity theory, but we didn't really have many examples. There were some nice examples, but they were sort of a bit special and almost like curiosities. Maybe some examples to do with number theory. Then we had the theory of Bayer's theorem, and there's a picture of Bayer's, who was, I think he was originally Finnish, but he spent the latter part of his life in the United States. Originally he worked on fluids, but he got drawn into this subject. So, well, okay, there was this that was pretty much, not many examples, but we understood something. Something was understood here. These were a complete mystery, except Bears and the work of a few other people said there must be some funny things which don't fall into this category. So there are some that we don't really know anything about at all. So that's where we were at. And then William Thurston came along. So in the sort of late 70s and early 80s, Thurston started, he came into this subject and he started proving just incredible theorems. Remember, in 2D, we knew that every surface had a certain kind of geometry attached to it, either Euclidean, hyperbolic, or spherical. So the first thing that Thurston began doing was he started taking lots of three-dimensional manifolds that the topologists kind of understood, but only in terms of topology. They didn't know anything about, they didn't have anything to do with geometry. He just took these sort of abstract constructs of topological objects, and he showed that actually you could impose, or that in a natural way, a hyperbolic structure. You could make this basic crystal that you could glue up, and you could make it hyperbolic. So I don't have time to tell you what is very technical, what classes of manifolds, but really very large classes. And this was completely astonishing. Nobody had imagined anything like this before. One of the classes was if you take 3D space and you draw some complicated knotted loop, and then you drill that out of space and throw it away and take everything that's left, that's a manifold. And he showed that most of those are actually hyperbolic manifolds in a very precisely defined sense. So he then went even further, and he made something known as the Geometrization Conjecture that you might ask, is it possible then that there's a way of putting geometry on every three-dimensional manifold? We could do it in 2D. Well, you know, nobody before him conceived anything like this, but he conjectured that in view of all the things he'd already done, and he'd shown were hyperbolic, that actually, not that there was a particular geometry on every manifold, but that after you, so just as if I take a curve on a surface and cut it, it opens out. If I, for example, draw a torus inside a manifold and cut along that, I'll get two bits of manifold, the bit that's on one side and the bit on the other. And maybe the bit on one side and the bit on the other side separately have some geometry. So that's what he showed. And he also showed there are only 8 types of geometry, and they're all quite simple. And in particular, we've got spherical, Euclidean, and hyperbolic. And actually, so he conjectured this was true. He didn't prove it. To just give you a sense of how sort of what an immense conjecture this was, I'm sure many people have heard about the Poincare Conjecture, which I will come on to. Let me not say what the Poincare Conjecture is right now. People may have heard of it, but the Poincare Conjecture was a problem that throughout the 20th century was basically driving mathematicians nuts. So and Thurston, he not, to me, it's not only that he proved these wonderful theorems, but he introduced all sorts of wonderful concepts. He was a very visual, hands-on mathematician. Sadly, he died quite young. Well, not young, but I mean, he was not old, you see, a couple of years ago. But he was always tremendously keen on getting students and school children and so on doing things by hand and making shapes and playing with shapes and so on. So he left an enormous legacy of ideas, and he had, so let me show the next slide. So by the time Thurston had been working with a large group of students who were attracted to work with him, what had happened in finite volume closed manifolds, well, an enormous amount. From being a few isolated examples with a good theorem, Mostow rigidity, it became a huge, big subject, huge, big area. Large classes of manifolds are actually hyperbolic. And a great deal of effort went into writing up sort of nice versions of his proofs and so on. Here's a picture of Thurston more recent. There was a big conference on his 60th birthday, and all of these students of his have them in themselves made large contributions to mathematics. So this case, well, let me just say it was recast from a subject that was mainly about Möbius maps out at infinity into something to do with topology and geometry in 3D. And this rather mysterious thing that must exist, well, Thurston did not solve the problem, but he began to tell us what to do. So what has happened since the year 2000? Well, these two conjectures, which I haven't yet told you what the Poincare conjecture is, but the Poincare conjecture and this Geometrization Conjecture, which is much bigger and includes the Poincare conjecture. Then there are three things whose names won't mean anything, but three other very important things which Thurston and some of his school put together, that between them, if you understood this, you would have understood this mysterious exotic case. And people really didn't know how to do this stuff. Maybe they had a little bit of idea about how to do this, as I'll show you, but really, beyond that, there was a lot of unknown stuff. And what have we done? Just to show you, mathematicians have been quite busy. So famously, with an enormous amount of press coverage, Grigory Perelman proved the Poincare conjecture. I mean, it depends when you think a theorem was proved. From the time the person first announces a proof to the time when it gets checked and possibly published can be really quite long in mathematics, so dates are a little bit. So Perelman proved this Poincare conjecture, whatever that says, and then based on these methods, this Perelman went further and he explained how to use his ideas, which were completely coming from a completely different direction, to prove geometrization. He left some gaps that have been filled in. Then these three things, all of these were large pieces of work. So we've kind of done it all, everything. Right, so let me tell you in a little bit more detail what's the Poincare conjecture. The Poincare conjecture in 2D, if I draw a loop on a sphere, I can shrink it down to a point. So I could ask the opposite question. If I had a surface such that any time I drew a loop on it, I could shrink it down to a point on the surface, would it be a sphere? And that's part of how you classify surfaces. So it's true that if I gave you a surface, and every loop that you could draw around the surface, so here's a torus, I can draw a loop, say this orange thing round here, and no matter how I move it around and stretch and twist, I will never get rid of it. I can't shrink it down to nothing. So I can detect, if I was a fly, I could detect whether I was on a sphere or on the torus by looking at these loops and could I shrink them down or not. So an innocuous sounding thing, supposing I went up to 3D, I had a three-dimensional thing. If I was in a three-dimensional sphere, I could do the same thing, could shrink everything to a point. What happens the other way around? If I could shrink everything, would it be a sphere? Well, you might think that wouldn't be so hard, but actually, it's incredibly hard. It was really incredibly hard, and all sorts of people tried, and there were many sort of incorrect proofs that were announced, and then people worked hard and found the mistake in them, and this went on and on. Another slightly strange thing in mathematics, you might not be able to do something in 3 dimensions, so let's try and go to higher dimensions. Maybe it's easier. And it's kind of easier because there's more space. So it's harder to think about it, but you don't think about it. You can just move things. So you can kind of move things out of the way and move them around each other, and so it could be proved in dimensions greater than or equal to 5, and then it was proved in dimension 4, and it was still sitting there unsolved in dimension 3, and some big prizes, the Clay Millennium Prizes, were set up just before the year 2000 of some outstanding problems of mathematics. There was going to be $1 million prize for the solution of any of these. The Poincare Conjecture was one of them, and, well, just about the time Grigory Perelman, you see here, proved it. And he used, I'm not an expert on this at all, but his methods were completely different. He started with not a homogeneous kind of metric at all, but a way of measuring distance that was just sort of anything, and as a clever way of kind of smoothing it out and smoothing it out and smoothing it out, and you come to sort of singularities, and you have to get random cleverly, but eventually you proved that this thing that you didn't know was a sphere has to be a sphere. And then he went on and outlined how to prove geometrization and using similar methods. And as I say, there was some gaps, but they've been filled in. Okay. And then we have the other three conjectures, which is more the direction I've been involved in. So here's a picture. One of the things Thurston did, he didn't have time to write up his stuff nicely, just throwing out ideas every day. But there is a huge volume known as Thurston's Notes, which were lectures he gave and were typed up. And the sort of beginning part has now been very beautifully edited and filled in and produced as a book. The latter part is still sitting there. You can find it online, of course. Here's a picture about, so we've got this manifold with infinite volume, and the thing is, what he said it looks like, you really don't know what happens as it goes off to infinity. But what he said it might look like is this. You might have a surface and then just take copies of the surface all the way going up and create a three-dimensional object. So just like you can take a circle and then a line and make a cylinder, you can take a surface of some kind, genus 2 in this picture, and go up and you make a 3D thing. And the key point, really, was that as you go out along here, in these weird examples, these exotic examples, there would be geodesic loops that wouldn't be getting very long all the way out along this thing forever and ever. So on the face of it, this end of this manifold, this infinite volume bit we couldn't understand, might have done anything. It might have been twisted in all kinds of terrible, wild ways, but actually he sort of tamed it. And this tameness conjecture says that, well, maybe it always looks like this. So Thurston showed in certain cases it looks like this. And then Thurston also showed that, well, how would you recognize which type it was? It turns out these curves that go, sort of lie on these surfaces, these geodesic loops that go out and out and out, you can sort of think of them like rational numbers, and they have a limit, which is some kind of irrational number, an object Thurston introduced called a geodesic lamination. And what he conjectured was, if you knew what the irrational numbers, as it were, connected to each of these ends were, then you'd know everything. Well, that seems pretty remarkable, but actually, turns out that's true. And not only is it true, if you know what happens on the ends here, actually, you can more or less reconstruct everything that happens in the middle. And this was not Thurston. This was largely Yair Minsky working with various other people, introducing some really beautiful mathematics and understanding the kind of coarse geometry of the whole hyperbolic manifold just from a very small amount of data about the ends. And then finally, well, could there be any of these things kind of sitting out there? We don't know where they are. Well, the answer is no, they couldn't. They'd always have to be limits of ones that we knew about. And it turned out that once we kind of got this far, this bit was fairly routine, quite routine, but it was more obvious to see how to go about proving that, so that was also proved. Right, well now, I don't know if I have time, but let me try to go very quickly through. So you might say we've solved all the problems. So one thing I didn't say was these three-dimensional things, you can put geometry on them. We know a great deal now about the geometry examples. It actually turns out that if you, in many senses, pick a manifold at random, it's going to be hyperbolic. Just as most surfaces are hyperbolic, so in 3 dimensions, by far the most common thing to happen is for your manifold to be hyperbolic. So hyperbolic has gone from being a kind of slight sideshow to something really fundamental. And I would say we're at a point now where we kind of understand that, but I said that surfaces were used, for example, to develop things to do with chaos theory. People are playing now, but I think the facts we now know about these three-dimensional things are surely going to come into play in the future in ways that we haven't as yet understood. Okay, so, well, very fast. Okay, so discreteness. So discrete means that you can move things away. If you've got rigid motions of some tiling, you can move the tile away from itself and it never comes back and hits itself. On the other hand, if you start rotating thing and you go around an irrational angle, an angle that's not commensurable with 2 pi, then you can go around and you'll come back, but you won't come back exactly on top of yourself, and you'll keep going round and round and round, and you'll end up producing a picture like this, and the longer you go, the more you'll overlap yourself. So being discrete is kind of nice. Let me just skip here, and let me just show you my last slide. So I don't have time to tell you that, but let me just leave you with this last picture. So just a picture of what it looks like to fly around in three-dimensional hyperbolic space. This picture was made by this geometry center, which was part of the offshoots of all the flurry of activity around Thurston's work. So I'll leave you there. Thank you very much.
What would a galaxy or solar system look like in a universe with hyperbolic geometry?